into our device, into our product. And the second trend is the pervasive connectivity and the development in the communication technology. So right now, the communication costs are getting very low. We can send our data to the centralized cloud and do a centralized processing. So these two technological trends provide great infrastructure for IoT technology. And enabled by these two technology trends, we can collect data from the devices in the field. And the third trend is the real-time data analytics. So using this advanced algorithm, we can convert the data into decision to optimize the system operation. So the IoT technology bring in a lot of new capabilities. At a very low level, we can collect the data from the in-field device and monitor the working condition of the device. So do the monitoring and the diagnosis to detect abnormal working condition. And in the intermediate level, using the data, we can make a prediction. So we can predict what the future behavior of the system, then adjust our operation decision to optimize the system operation. And by looking at the utilization pattern of the device, we can even provide feedback to the design to optimize the system design. So the ultimate, this IoT technology can enable us to achieve autonomous smart system. So one example is automotive, like a self-driving car. So this is the ultimate example for IoT-enabled smart system. And on very high level, what are the main data types we can collect from IoT system, from industrial IoT system? So in my view, the data type can be classified into two categories. So the first category is the usage pattern of the device and the product. So how customers are using the product, using the device. So like on-off, like for example, for air conditioning. So we know the on-off control, we know the temperature setting, etc. And for kitchen cooking device, so we know when people are using this cooking device and what are the recipes that people are cooking with the device. So this is one category of data. With this category of data, we can really get this data-driven knowledge on how people using our product, so to optimize the product design. And another set of data is the equipment condition monitoring. So we can collect the physical signals from the device and monitor its working condition. So with those two types of data, we can improve the system design and improve the system productivity, safety, reduce the cost, and improve the achieve the sustainability. But there are some critical challenges in this IoT data analytics. Like if we want to convert the data from the data-rich environment to this smart decision, so we need to overcome several key challenges. So the first challenge is the big data. Because in an IoT system, we often collect data from a large number of devices and products in the field. So the data volume typically is high. For example, in a typical automotive IoT system, like in the OnStar system from General Motors, so in 1 month, they could collect terabytes of data from all the cars in the field from General Motors. So it's a large data set. And the second challenge is that we have a pressing need for information fusion and individualization. So one characteristic of those IoT data is that we collect the data from a large number of similar devices. So this creates opportunity. So we can learn from each other. We can learn from other devices' data and try to make decisions, help the decision making for the current device under study. So we need the information fusion. We can learn from each other, collect the shared information, get information from shared data. But on the other hand, we also need the the model individualization, that we want to make decision for individual device. So this is both an opportunity and a challenge. So the third challenge is the diversity and the heterogeneous data. So in the IoT system, the data collected is often this diverse, have a different type. We often have a continuous measure. We also have a lot of event data. We also have a categorical data. So the data type is really diverse. The last challenge is in industrial IoT system, we often need to make a real-time decision. So that means, although we can do offline modeling, but when we make decision, make a prediction, often the decision need to make in a very short time, in real time. So we need to have a very efficient computational algorithm to achieve that. So to fulfill this promise of industrial IoT system, we need to develop new methodology and to take advantage of the data availability and overcome those challenges. So here I will introduce 3 topics we have been working on along the industrial IoT data analytics. So the first topic is the data-driven statistical prognosis and service decision-making for teleservice system. So this project is in collaboration with the General Motors. Essentially, we work on automotive IoT system. So we collect data from the cars in the field and try to predict the critical failure, predict catastrophic failure to the critical components. So one specific this component we're working on is a car battery. So it's acid battery. It's in charge of starting the car. So if the battery going down, the car we will not be able to start the car. So the customer will be stranded. So it's a critical component, although it's not a very complex component, but it is a critical component in the automotive system. And the IoT system we're working on is OnStar system. So if you own a GM car, you will know all the GM cars have this system. So the system, through the system, the driver can communicate with the operator, and the system also collect the condition monitor signal from the car and send back to the cloud. So the General Motors service engineer can make prediction and send out a warning to the customer based on the data collected from the system. And for the battery, we specifically collect some degradation signal, so such as internal resistance, capacity, etc. So those condition monitor signal, we call degradation signal, a continuous temporal signal. It's a longitudinal signal we collect a long time. And it is gradually getting bigger and bigger. Once it's larger than a certain level, it's an indicator, like we have a high probability the battery will not be able to start the car. And another type of data is the failure events. So it's a record the event that the car battery fails. So for specific car, those failure events is very rare. So typically in the whole lifetime of the automotive, maybe once or twice. But because we monitor a large amount of automotive in the field, so we have a kind of decent amount of such event data. So the idea is how can we incorporate those 2 types of data together, some real failure event data and some degradation signal data, so we can combine, fuse those the 2 data types together and make accurate prediction. So in this project, we propose a joint prognostic model. So this model incorporates these 2 types of data together. So one model is called the mixed effect model. Essentially, it's a model to describe the degradation signal and make prediction of the future degradation signal value. Another model is a classical survival model. It's called the proportional hazard model. Essentially, it's a Cox proportional hazard model. So this model make a prediction of the failure event occurrence. So this model dealing with failure event data. This model dealing mixed effect model dealing with continuous degradation signal data. So for the mixed effect model, for the degradation signal, we use a mixed effect model. You can view the mixed effect model as an extension of a single regression model. So a single regression model to describe one signal path. But for mixed effect model, you can view it describe a population of a signal path. Essentially, the model coefficient in the regression model is a random variable in the mixed effect model. So, and this random variable follows certain distribution, and the distribution of this random coefficient describes the population behavior of this group of signals. So for each signal, we have a different parameter, and for different signal, we have a different parameter, and those different parameters form a population distribution. And with this model, we can describe a whole group of divergent signals. And this is a very effective way to fuse information from multiple signals and allow the individual behavior for individual signal. And for the proportional hazard model, it's in this advanced regression model format. So the output of the model is the hazard of certain events. You can view the hazard as a kind of instantaneous probability of such. And we have a baseline non-parametric hazard function, and we have a covariance path. The covariance could contain time-fixed covariance or include this mixed effect model as its input. So essentially, we use the mixed effect model to predict the future value of the divergent signal, and then use the predicted future value of the covariance to predict the future occurrence of the failure events. So this is the intuition of this joint model. And this slide shows the property of this, shows this behavior of this model. So essentially, the red line is the predicted degradation signal. The red line here is the predicted survival function of the critical failure events. So essentially, give us the probability that the system will survive beyond this time. And the blue dots are the observed degradation signal from the system. And the dashed line is the underlying truth. You can see with more and more observation data coming in, our prediction of the survival function and the degradation signal getting more and more accurate, eventually become consistent with underlying truth. And the bottom three panels are the Bayesian illustration. Essentially, we use a Bayesian approach to update the model. You can see the model parameter updating. This shows the posterior distribution. You can see the posterior distribution will convert to the underlying truth. So this is how the model will work. And we also test this model underlying the using a true data set, true underlying data set. So we have this prediction error. You can see the prediction error is much more smaller than the other method, particularly at a later stage of the life of the battery. So we are much more accurate than the other method. The other method essentially is the threshold-based method. We only check the level of the degradation signal. If it's past certain level, we claim the failure will happen. You can see the accuracy is not as good as this joint model approach. And in this joint model approach, we use a mixed effect model to describe the degradation signal. Essentially, the mixed effect model is the extension of a parametric regression model. But one challenge in practice is that the degradation signal really exhibit very complex behavior. So in that case, it's really hard to find the parametric regression form to describe the degradation signal. So we could specify quadratic polynomial, we could specify exponential type of function, but in reality, the degradation signal does not behave anything like that. In that case, if we force the parametric regression signal in the mixed effect model, we will have a large prediction error for the degradation signal. So another work we try to do is we use a non-parametric way to describe the degradation signal. So essentially, we use a Gaussian process approach to describe the degradation signal. So in that way, we don't specify any pre-specified parametric form for the degradation signal. So it's very flexible. Hopefully, it's more powerful to describe the degradation signal. So let's look at the details. So the key setup of the model is a multivariate Gaussian process model structure. So assume we have historical degradation signal R1 to Rn. Those are historical degradation signal. And it's described for each degradation signal, it's described by fix the regression part. This could be a constant value or could be a quadratic form, etc. And also plus a Gaussian process, F1 through Fn, each one is a Gaussian process, and plus a noise, like a measurement noise, IID noise. So if we have a dense measurement data, actually we can simply specify the regression part as a 0 or any constant value. So this doesn't matter. So this term will only play a role if we have very sparse measurement. Like means we don't have too many measurements from the historical signal. Then in that time, probably we need to specify some this so-called mean function for this Gaussian process model. So the feature of this model is that we have multiple Gaussian process model involved. Assume we have n historical degradation signal and one signal under study. We want to predict the future value of RR. Then we have n plus 1 Gaussian process model involved. So the question is how to specify the structure of those Gaussian process model and how to use it, help us to make prediction. Let's look at the intuition of Gaussian process model-based modeling and prediction. So the Gaussian process model essentially is a very effective way, widely used in statistics and machine learning for functional data modeling. So you can simply view a Gaussian process as a bunch of random variables, normally distributed random variables. And it's a very nice non-parametric way to describe a function value. And the key parameters we need to specify for Gaussian process is the covariate function for the Gaussian process. So essentially, intuitively you can view the covariate function specifies the similarities of the random variable of the Gaussian process with the different input. So typically, the Gaussian covariance function takes the input of the Gaussian process as the input and provides the covariate value of the corresponding Gaussian random variable of the Gaussian process. So if the covariance function is indicate the covariance is very small between two random variables, then the similarity between these two random variables will be less. So we will have high this variability in the Gaussian process. We will end up with this jiggly-wiggly type of function, have high frequency type of feature. But if we specify the covariance between two inputs of these two Gaussian random variables are very high, that means these two random variables are very similar to each other. So we will get a very smooth curve. We will get a very smooth this Gaussian process function. So you can see, by specify different covariance function, we will end up with quite different characteristic of the functional form. So Gaussian process is a very flexible way to describe this functional data. And now the question is, if we have multivariate Gaussian process, so we use this Gaussian process model to make prediction. What's the intuition behind it? So this picture illustrates the intuition. Assume we have 3 signals. We want to predict the future value of the middle signal. And we have 2 historical signals, upper signal and the lower signal. And essentially, using the multivariate Gaussian-based prediction, we're using a weighted average of all the observed data points to predict the future points. And the question is how to decide the weight for each observed data points. And the weight is determined by the covariance between this point and the corresponding predicted point. And this covariance is determined by the covariance function. So essentially, to make a prediction for this point, we need the covariance function for this Gaussian process, for the middle Gaussian process, to decide the weight for these 3 points to these predicted points. And we also need the cross covariance between the upper Gaussian process and the lower Gaussian process to the middle Gaussian process to decide the weight of this historical observed, the observed data points from the historical process to the predicted points. So the key is that we need to specify or to estimate a good covariance function. The autocovariance function for the middle process and the cross covariance function between the other process to the middle process. So this is the intuition for the Gaussian-based, multivariate Gaussian process-based prediction. So in this work, we propose to use this convolution process to construct a Gaussian process, and then use the structured convolution processes to construct the multivariate Gaussian process covariance function. So essentially, it's known that a Gaussian process can be viewed as a white noise process convolute with the smooth kernel function. So we end up with a colored Gaussian process. And the colored Gaussian process essentially is the Gaussian process. So in this equation, the X is the white noise Gaussian process. It is also a Gaussian process, but for at any different input points, the corresponding Gaussian random variable are independent from each other. So it's a white noise. So any point is not correlated with any other point in the process. This is the X process. And the K here is a smooth kernel function. So once we convolute this X through this kernel function, we end up with a colored Gaussian process. So its covariance function is not like a Dirac delta function anymore. It's a covariance function have a structure, and its covariance function could have a one-on-one mapping to the kernel function. So if we know kernel function, we could derive its covariance function. Or if we know its covariance function, we may derive this kernel function. Of course, not for any kernel function we can have a closed form covariance function. Only for certain simple kernel function we may derive this covariance function. So in this way, we can construct a Gaussian process. And if we have a data collected from this FI process, we can estimate the kernel function parameter. So this is a way. But why we want to use this way? So we can use this convolution construction to construct the multivariate Gaussian process. So first, for F1 to Fn is corresponding to the historical degradation signal. So each one is constructed by white noise passing through an individual kernel. So this F1, F2 up to Fn are independent white noise. So F1 to Fn are independent from each other because they're not connected from each other in any way. So they have independent driving white noise. They also have independent kernel function. So they're independent from each other. That means the behavior of F1 to Fn could be quite different. That means in the historical data, we could have quite different degradation signal form. And for the construction of FR, which is corresponding to the signal under study, it's more complicated. It have an independent part. This one is independent from any other constructed. The XR is independent from anything else. KR is independent from anything else. But it also have a shared part, like F1 shared with F1 and FR. So the F1 and FR could be correlated. So we allow the cross correlation between F1 and FR. In that way, when we predict FR future value, we may borrow information from F1. We may borrow information from F2 up to Fn. In that way, we can learn information from this historical degradation signal. So in this construction structure, we can achieve that. And we can derive to make a mapping between the covariance function of this multivariate Gaussian process and the kernel function. So we have K11 to KNN plus this K1R to KNR plus KR. We have a relatively larger number of kernel functions. We can mapping this kernel function to this covariance function, then write up the electrical function, and with the historical data observation and the current data observed from the FR, we can estimate the parameters in the kernel function. So in that way, we can get this offline estimation and set up this multivariate Gaussian process. After we get this parameter estimation, we can do the prediction. And the prediction actually is similar to the single univariate Gaussian process prediction. Essentially, we use the covariance between the point we want to predict and the existing observed data points, and use all the observed data points to make the prediction. So this is essentially the formula. The formula looks complicated, but it's very easy to interpret. We can not only predict its future value like R, we can also get the uncertainty in the prediction. So like how much confidence in the prediction. So this is identical to the univariate Gaussian prediction, but the covariance structure is much more complicated. So this essentially is one new idea we developed using the multivariate Gaussian process to make prediction for arbitrary functional form degradation signal. And we did this comprehensive comparison, use a simulation study and use real data. You can see we compared with this mixed effect model-based method, like the method we used in the previous work. And we can see if the model assumption in the mixed effect model is correct, like we found the right underlying parametric form of the degradation signal, then the Gaussian process method performance is slightly worse, but also pretty good. The mixed effect model-based method is the best. This is not surprising because we have a limited number of parameters to estimate in the mixed effect model approach, and the underlying function form is correct. Of course, we get the best estimation and prediction. But if we have a misspecification, the underlying function form of the degradation signal is not the same as the assumed functional form in the mixed effect model. The performance getting worse. So our Gaussian model-based method is better, get better performance. So, and we're also better than other methods like this functional PCA type of method. And in this testing, we assume in the historical data set, we have a different type of functional form. So some function degradation signal might be degraded monotonically. Some may have variation, sometimes going up, sometimes going down. So we have different type of functional form. This is very hard to handle for other type of method. But our Gaussian-based method can handle that. So essentially, we can learn how many different type of functional forms in the historical data and find the right kind of functional form to learn, to fill the information. So the performance is still kind of satisfactory. And we also tested this method using a real data set. This is a real data set for the battery data. You can see the degradation signal form is really wild, it's really diverse. So have a different type of form. It's really hard to say what functional form is really follows. You can see our prediction error for this MGP is multivariate Gaussian process-based prediction. You can see it's much better than other methods. It's 2 to 3 times better than other methods. So it's a pretty flexible technique. And it's a pretty general, not only applicable to degradation signal, but also to other temporal signal prediction and modeling. So this is the second technique. So in the third technique, due to time limit, I will go through it very briefly. The idea is that we want to fit the interactions between a bunch of random variables using a transfer learning technique. So in IoT system, we often collect data from multiple components within the system. And sometimes we're interested in this detect the interactions or interdependence among the data collected from different components within the system. And a typical example is in this multi-stage manufacturing process. And using this, take advantage of the data availability, we may use a graphical model approach plus a transfer learning technique to fit this model with a limited amount of data. So particularly for this new process, let's take a look. What does that mean? So the graphical model is a very powerful statistical tool to describe the joint distributions of multiple random variables. So essentially, in a graph model, we have nodes and edges. the edge could be directed or could be undirected. In this work, we mainly consider this directed edge. So the node in a graphical model represents the random variable, and the edge in the graphical model represent conditional dependence between different random variables. For example, in this graph, we know the grade a student obtains is conditional dependent on the difficulty of the test. Conditional dependence means if we conditional all the random variables in this graph, we still have relationship between the difficulty. There's some unique contribution of the difficulty to the grade the student will get. So intuitively, that's correct. So essentially, this one can give us some insights to the unique relationship between different random variables in the system. Or in the engineering system, give us the relationship between different components within this system. And with the graph structure, we can decompose this joint random distribution into multiplication of some simple conditional random distribution. This is the decomposition without graph structure. You can see the decomposition is relatively more complicated. We have a lot of conditional variables, but here the conditional variable is much less. So it's a simpler decomposition. So the idea is how can we fit the multiple random variable with this graph model. And the application, a typical application is in multi-stage manufacturing process. Let's take a look. Like for multi-stage manufacturing process, we produce the product at multiple stages. And at each stage, we may have some key product characteristic, like a quality measure. Like in assembly process, we may have a dimensional quality achieved at a different stage. And clearly, the earlier stage performance will potentially impact on the following stage performance. If we didn't assemble it correctly in the previous stage, in the following stage may cause some other assembly error, or this make some related components even worse. So we have this multi-stage manufacturing process have potential interactions between different stages. So for quality control or process monitoring purposes, we often need to monitor or to establish, to find out what are the unique relationships between different quality characteristics at a different stage. So we want to find out this conditional dependence between different stages. So with that information, we can monitor, diagnose the manufacturing problems more effectively. So this is our goal in this work. And particularly, we want to fit a graphical model called this learn the structure. We want to learn a graphical structure called this ordered block model. So the ordered block model is a special case of a graphical model. Essentially, we can put the nodes in the graph into different stages, and the influence or the edge between the nodes can only point from the previous stage to the following stage, like this one. So we will not have an edge point backward. You can see clearly this is a special case for general graphical model. General graphical model is any two nodes could have an edge, but here the edge could only point from previous stage nodes to the later stage nodes. So it's a special case of a general graphical model, but it fits this multi-stage manufacturing process case very well, because we know in multi-stage manufacturing process, the influence can only go from the previous stage to the following stage. So not vice versa, because once we fabricate stuff in the following stage, the previous stage is already fixed, it's already done. So no way we could have backward influence a long time. So similarly, for some other temporal process, so we can set up the random variables into different stage a long time. So only the previously occurring events have influence to the following stage events, not vice versa. So although it's a special case, but it have a pretty broad application. So And now the question is, how can we fit the structure? Like based on the observed data from the random variable, we sample the random variable, got a bunch of observation data. How can we fit the conditional independence relationship within this graph? And if we have a large amount of data, we can do this. You can imagine we can do this testing. We test the independence between random variable or conditional independence. And based on the testing result, we draw those graphs. But the trouble is what happened to a newly established process. We don't have too many data. So how can we set up, get the structure quickly without limited data? So the testing will not be very efficient. The power of the testing will be weak. So we will have a lot of mistakes in the testing results. So how to do it? So we want to use a kind of transfer learning type of technique called information sharing. The idea is that if we have a similar process, we have a historical similar process. We already collected a lot of data from the historical process, and we fitted the historical structure. Can we learn from the historical structure and to help us to find out the structure of the current process with the limited data collected from the current process? So this is the question. This is the problem we try to solve. A simple kind of check of the problem formulation, we'll see there are some challenges. So this is illustrated by this picture. The first challenge is the inconsistency in the historical process. For example, we have two historical processes. In process 1, 2 and 5 have a link, but do not have a link. But in process 2, 2 and 5 have a link. So in that case, how can we make decision for the new process? Should we put a link between 2 and 5? So how to learn, how to fuse these two conflict pieces of information together? So the second challenge is that we have this inconsistent sample space. So in this historical process, we have a new node 3, but here we don't have a node 3. In the new process, we have node 2, but we don't have a node 2 here. So how can we make this sampling space consistent from each other? That's another challenge. So third challenge is so-called negative transfer. This is a typical challenge in transfer learning. That means if two processes indeed are similar to each other, we could help the learning. But if two processes are quite different from each other, we need to be careful. If we force the learning, then actually the learning result is even worse compared with not consider the historical information at all. So this is called, we should avoid negative transfer. So consider this 3 key kind of challenge. We develop a systematic methodology based on the Bayesian approach. So to learn, to do this transfer learning, to overcome those 3 key challenges. The problem formulation is like that. So the key idea is that we treat the graph structure as a categorical random variable. Like in this case, we have 3 nodes, and we could have 3 different realizations of the graph structure. So we can view the graph structure G as a random variable. It could possibly take those 3 different values. It's a discrete random variable or categorical random variable. And the learning, structured learning, essentially is that we want to find the posterior distribution of this graph random variable by observing the data. And using the Bayesian formulation, we found out essentially the data likelihood, the posterior distribution proportional to the data likelihood multiplied by a prior distribution of the graph random variable. So if we don't consider the historical data, essentially this pi g is the user-specified prior distribution. We can simply specify a uniform distribution, uniform categorical distribution of this one. So this becomes a non-prior distribution, and non-informative prior distribution. So we don't take any vote on this 4 possible structure. But with historical data, we can learn the prior distribution, so become an informative this prior. So essentially, through a simple derivation, and we assume the data collected from different processes are independent from each other, we can get the same kind of formulation. So this data likelihood. This D is collected from the new process. D1 and Dn are data collected from the old process. So you can see this is in the place of the prior distribution. Essentially, instead of manually specify the prior distribution of the graph random variable, we learn it from historical data. And in this work, we developed the whole learning process, how to learn the prior distribution of the graph random variable. Essentially, the key idea is that we assume the graph random variable for different processes follow the same categorical distribution. Essentially, we try to learn based on the observed data from the graph. We learn the categorical distribution. So it's the derivation is pretty involved, but the concept is relatively easy to follow. So I skipped the details, and we did a simulation study and real data testing to see the effectiveness of the learning. Here is the learning result. You can see the blue line is without transfer learning. The red line is with transfer learning. The vertical axis is learning accuracy. Essentially, the percentage of edges we learn correctly. So the horizontal axis is the number of samples we need. So number of samples we need. You can see if we have a large amount of samples, eventually we can learn 100% correct about the graph structure. But if we have limited amount of data, this the transfer learning can learn very quick, get very accurate this learning result. This NE for different measure is measure the similarity between the historical process and the current process. So if the historical process is very similar to the current process, we can learn very quick. Transfer learning is very effective. But if historical process is quite different from the current process, the transfer learning does not help too much. So that also makes sense. So, and we also applied on a real process. So real multi-stage assembly process. We can see this learning effectiveness is 2 times quick. So we can achieve same accuracy with half of the data if we use the transfer learning technique. So here is the summary of this webinar. Essentially, I believe this Internet of Things is the emerging technology, is the foundation driver for Industry 4.0. Like there are a lot of research opportunities in IoT-enabled data analytics, in IoT-enabled this engineering problems. So I encourage the people in quality statistics and the reliability division to pay attention to this direction and try to contribute to this area. Okay, thank you for your attention.
Well, thank you, Dr. Zhou, for the great presentation. Now we will take questions. If you have questions, please type the Q&A panel and type in your questions, and so we all can see. There was already one question typed in when Dr. Zhou was giving the presentation. David Heyman asked, will the slides be available?
Okay, yeah, I will make it available. I will send to this Lincoln, and Lincoln you can find a way to share this one.
So maybe I can post it on Informs Connect.
Okay, I will. There's some confidential kind of information. I will remove that, but the basic structure of this presentation will.
Okay, great.
Most information will be in here. Yeah.
Thank you. Thanks for being willing to share the slides. Any other questions? Dr. Zhou, can you see the Q&A question?
Yeah, I can see.
Okay. Then please feel free to answer yourself.
Yeah. So the question is, I have not understood how you manage non-uniformity in the process stages. So my question is, for this question is regarding which piece of work is with the Gaussian process work or with the graphical model work, this question is regarding which segment of the work. Okay, I don't know this. Okay, the second question is applications for urban computing and smart city case studies. Is yes, of course. So for the IoT, this applications, there are tremendous amount of applications in this smart cities. For example, with IoT, we can detect empty space in the parking lot, so we can guide people to find the empty space quickly. There are a lot of application cases. Unfortunately, I myself am not involved in such application. I have some case study on this restaurant operation with IoT-enabled technique. But for the general urban transportation, urban this energy infrastructure type of thing, I myself don't have that. But there are a lot of tremendous amount of applications in that area. So the third question is, what's truly different between current IoT and the previous sensor network research? This, okay, this is a good question. So in my view, there are two major differences. The one difference is previous sensor network type of research. The type of data is kind of limited. It's very specific. They're suited for one very specific this application area. So for example, it detects the existence of some targets in some military application, or we deploy sensor network to detect the earthquake type of thing. So that means, but right now the IoT system, the sensor network, we have essentially the communication bandwidth is much bigger than the previous sensor network. We could collect a lot of different type of data. Event data, continuous data is a really very comprehensive data set. The data capability, the data variety is much more than before. The second difference is the computational power. So we can put the data into cloud, and the cloud computational, the scalability is much better than the sensor network type of research. The research focus are quite different from the sensor network. Okay. Okay, so right now the question is, I have two questions. Have you published the result of, yes, yeah, we have some publications along each of those topics. And I will put the relevant publication title in the presentation, so you can see that. Some publications still under review, so this, but some is already published. And the last one is share the recorded video. For that, I don't know. I don't know if Lincoln, you record the video or not.
Yes, I recorded the video. So all the videos and the slides, thanks to Dr. Zhou for willing to share, will be posted on INFORMS Connect. So all the INFORMS-QSR members will be able to log in to INFORMS Connect and download this.
Okay. Okay, the next question is from Dave Das. Is that very limited in embedding computational power? Will that limit? Will that does that limit how much useful information that can be sent back to the device? This, for me, my experience is that actually the computational power at the edge embedded in the device right now is pretty high. This is much better than a computer, than a desktop computer maybe 15 years ago. So this is not a major issue. The major issue is still the people struggling is what type of sensing data, what type of event data we should collect to help us the targeted decision making. So the hardware, the software, the communication speed, the computational power are not a limiting factor for now. The key is still the underlying physics of the process to guide people find the right sensor to use, find the right data to do. Okay. Okay. The next question is My first question is, what did you consider as a degradation indicator of batteries? Can you find the ground distribution of multiple factors such as DOD associated with the resistance of batteries? Yeah, this is a very good question. In our work, we use the two indicators. One is internal resistance. It's an important physical indicator. Another one is proprietary, is a confidential indicator. Our industrial calibrator just gave us this value, didn't tell us what it is. So in general, this create a good indicator itself is an important research topic. It's not easy. Like in general, if we incorporate multiple physical measures to form one indicator, the performance is in many cases is better than the single physical indicator. And there are some existing research in the QSR area, so you can look into those work. Okay. The next question is, can these models be cloud analytics like? Yes. Yeah. The question is, can these models be applied in real-time cloud analytics engine like Power BI in Azure or IoT data, where IoT data is aggregated? Yes, for the prediction part. So typically for those type of model, they have one complex model fitting part and have a relatively simple prediction part. So once we estimate those parameters, the prediction part is relatively simple. For that prediction part, we can use in real time and make a prediction. But for the model fitting part, typically need a large amount of calculation. That is relatively difficult to do real-time model fitting. So put it simply, for the offline model fitting part, we need to do it offline. For the online prediction part, we can do it online. Yeah. So, okay.
So, Dr. Zhou, here's a question from me, if I can ask a question.
Okay.
So how big is the data size when you're dealing with data from multiple sources?
That depends on the application. It's, the issue is the data set is large. It's often due to the constant data collection, like constant collection. It's once the IoT system is online, it's always online. Like during this the whole operation process for weeks, months, the data continues coming in. So it's not due to in one instance we have a suddenly large amount of data coming in. That's not. The speed of the data is relatively slow, but the duration of the data is very long. So once you accumulate those data, the data sets become large. That's my experience. In most cases, the data volume is large. It's due to the data collection volume, the duration, not due to the speed. So if you claim this big V, like the big data, the 3V, typically my experience with this current IoT system, they have a big volume, big variety, but not so high speed. Velocity is low. But there are some applications, the velocity might be high, like for self-driving car, because we need to make decisions in milliseconds. We may have a lot of this driving information coming in if we use a cloud-based self-driving. Yeah.
Thank you. Thanks.
Okay.
That answered my question.
Yeah.
Do we have any other questions? If yes, please type in the Q&A. So it seems like the presentation is already very clear and all the questions are answered. But we would like to thank Dr. Zhou again for the great presentation and service to the community.
Okay, thank you. Yes, thank you for your attention. So I enjoyed it.
Thank you. So the presentation is recorded, and the webinar is recorded, and the link will be available on Informs Connect. So please pay attention and check the website. And Dr. Zhou is very generous to share the slides. So I will also post the public version of the slides on Informs Connect. So please also check the website. Thank you all.
Okay, thank you.
Have a great day, Dr. Zhou.
Yeah, thank you.